been a focus on wire development, making the wire that gets wound in the magnet. When that progressed to the point where one could start making larger magnets that high performance, right, the challenge of protecting the magnet became more important. So the fundamental element of this technology is to have an internal distributed sensor within superconducting magnets so that one can measure temperature variations and strain variations as a function of time on a very, very fast time scale with very high spatial resolution.
So obviously, the bigger the magnet and the more important the quench protection also becomes, because the stored energy is higher, and so in the case of a quench, the damage will be higher. Again, the damage is proportional to the stored energy. So the more the stored energy, the more important the quench protection is. So especially, I would say, in the wind turbine sector.
It was really driven by understanding the internal processes in a magnet that can lead to failure, and then understanding what we need to sense to prevent it.
The reason for focusing on high temperature superconducting materials is in the fact that they have a way more challenging quench behavior. So the importance of the quench detection system is related to the fact that if a quench happens, first of all, you have to shut down the system. So whether it's an MRI or a motor or a wind generator or a particle accelerator, so you have downtime of the facility. Plus, very likely you have the loss of the equipment, so you lose the investment.
So the idea here is that fault conditions in superconducting magnets based on high temperature superconductors tend to be very localized and small, and they grow in magnitude, but they don't grow spatially.
It's due to the fact that the quench propagation velocity, so the velocity with which a normal zone propagates along the conductor, the superconducting conductor, is way lower. It's 2 to 3 orders of magnitude lower than in low temperature superconductors.
And so one needs a distributed sensor that can identify what's happening very precisely, location-wise, very quickly, so that one can protect an expensive system.
And it obviously also has an incredible advantage in terms of sensitivity and response time, because obviously having the optical fiber into the conductor provides an extremely good mechanical and thermal coupling between the fiber and the conductor itself. And obviously the conductor is the source of the perturbation. It's the source of the heat, the Joule heating and the strain. So having a very good mechanical and thermal coupling between the fiber and conductor is extremely important. And this is obviously maximized when the optical fiber is inside the conductor architecture. So that provides extremely high sensitivity, extremely high response time, no reduction in winding packet density, no change in magnet design. And so we think this is probably the most acceptable way for the community to start embracing the technology.
We're using release scattering with a 30 millisecond or faster timescale. And so it's truly a real-time distributed sensor. So that combination of high speed or high frequency and high spatial resolution is quite unique.
The sensing mechanism is strongly based on the fact that the fiber material itself is not perfect. So it's totally based on the defects and density fluctuations, voids, which are also density fluctuations in the fiber itself. And they provide scattering centers for release scattering. So they are at the core of the technique. So basically, since the fiber material itself is not perfect, all of these density fluctuations, voids, impurities, they are all scattering centers that will generate ready-based scattering.
We are at the point where we have shown that this works, that the concept works, the implementation works. So we're very much in what I would call the scale-up and transition stage.
We've made experiments with YBCO at both 77 Kelvin in liquid nitrogen, in vapor, so vapor-cooled coils, and about 77 to 85 Kelvin. We have shown that the optical fiber sensors are superior to voltage. And then we have also replicated and showed that the same advantages extend to lower temperatures, from 4.2 Kelvin in liquid helium up to 20 Kelvin, 40 Kelvin in helium vapor. Well, depending on the applications, the length of conductor needed for the magnet can be from hundreds of meters to kilometers, to tens of kilometers, which means that if we want to monitor the whole magnet with an optical fiber, we need to be able to acquire the optical fiber in kilometers of length. And that's totally possible because these are telecommunication grade optical fibers. So they are widely available on the market. They are very mature technology, and there's no very inexpensive. So there's nothing challenging from that perspective.
High temperature superconducting magnets need quench protection in order to advance to bigger systems, but we also need magnet systems to go into to demonstrate our ability. And so I see the progression being hand in hand, not one leading the other, but really the mutual need being the thing that helps propel it forward.
This technology is crucial in all the applications that require basically magnetic field, and that would benefit from using high temperature superconducting materials, especially YBCO and visco. And then, because again, all the high temperature superconducting materials suffer from a very difficult quench detection. So this technology has the potential to enabling all the applications that rely on basically magnetic field. So there are motors, generators, both for aircraft or ships or wind turbines, and obviously when applications where magnetic field is the core, like particle accelerators or fusion reactors.
It's nice when your peers look at what you did and say, yes, that's fantastic. And so, when a colleague who I've known for years, who's at MIT, who has a spin-off, says, if you make this work, we're ready to buy it. That's an exciting response, because that's communicating that not only what you're doing is successful, but valuable and impactful. And really that's what you want, in terms of the D side of R&D, is to not only have it succeed, but to have it have impact.